Okay, welcome back for part two of lesson 3.2 on rational functions, specifically asymptotes. Let's have a look at what we need to do now. So I'm going to share my screen. Okay, so last we left off, we were looking at vertical asymptotes and holes. Now we're going to look at horizontal asymptotes. So what a horizontal asymptote is it's a horizontal line, obviously, but we can define it very specifically, and we actually need to define it fairly specifically because our previous version of the definition where we said an asymptote is a line that the graph never crosses isn't always 100% true. A better description is to say when the end behavior of a graph is not rising or falling, but it approaches some finite value L. Don't worry about L for now, but instead of our graph, like all normal polynomials, maybe it'll do squiggle and then it'll shoot off to infinity and it'll shoot off to negative infinity. That's not what we're talking about now. We're talking about the end behavior actually ending up at some fixed value. So maybe our graph squiggles, but it ends up at some value, and maybe that value is 2 or 10 or whatever. But it approaches this very specific value, so it levels off. Then we say the line y equals L, because that's how we do the equation of a horizontal line. Okay, well that's just terrible writing, but anyway. So when it's a horizontal line, we call that a horizontal asymptote. So we can use a few simple rules to predict whether a rational function will have a horizontal asymptote. So for now, I'm just going to tell you the rules, and we're going to use them, but then we're going to think about it a little bit. So what we can say is if the degree of g is less than h, so the degree of the numerator is less than the denominator, then what we're going to have is the line y equals 0 will be a horizontal asymptote. So for the most simple one, y equals 1 over x, the degree of the numerator here, the degree is 0, the degree of the denominator is 1. And we can see that 0 is obviously smaller than 1. So what we can conclude is that this will have a horizontal asymptote y equals 0. Even if they get more complicated, 4x minus 2 over x cubed, blah, 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 this has a degree of 1, and this has a degree of 3. So what we can conclude is that this one's also going to have an asymptote, and we can see it levels off here and here at y is equal to 0. So as long as the numerator is a smaller degree than the denominator, y equals 0 will always be the asymptote for that. If the degree of the numerator is the same as the denominator, then you get a line y equals L, where L is the ratio of the leading coefficients. So this sounds like a mouthful, but it's actually really simple. If you look at this little guy down here, we have 4x squared, so that's degree 2. And then we have 2x squared, that's also degree 2. They have the same degree, but the leading coefficients here and here, it doesn't matter, these guys are totally insignificant in this process, but we have a ratio of leading coefficients. So the leading coefficient ratio is 4 over 2, which is 2. So this tells me the line y equals 2 is going to be my horizontal asymptote. And this printout here confirms it. My graph is leveling off in both directions at y is equal to 2. If the degree of the numerator is larger than the denominator, so the degree of g of x is bigger than h of x, you're not going to have any horizontal asymptotes as well. So I don't have an example for this one, but this could be like y is equal to x cubed minus 1 over x squared or something like that. Well, this one's probably going to just end up shooting off there and maybe going down like that. It's not actually going to level off. Okay, one little thing that's worth noting here. Note that functions can cross over horizontal asymptotes, but they can never, ever, ever cross vertical asymptotes. So it's definitely possible to have a situation where a function oscillates back and forth, but then it's finally going to level off. That means that this point here would be the horizontal asymptote, and it can cross a horizontal asymptote as many times as it wants, but it will never ever cross a vertical asymptote. The reason for that is we are picking x values independently, and remember, a vertical asymptote happens with non-permissible values, and non-permissible values literally mean values of x are not allowed to choose. You cannot make a graph across a vertical asymptote because there's no x value there. You're not allowed to even make it exist. But there's no restriction on horizontals. It's pretty uncommon for it to cross over. Normally it doesn't, but it still can. And as we can see in this example, it definitely goes up and over and then comes back down. Okay, so determine the equation of the horizontal asymptotes if there are any. So what we do is in a question like this, we have to look at what's the degree of the numerator versus the denominator. The degree is always the largest exponent, so this one has a degree of 2, and this one has a degree of 1. Because the numerator is a larger degree than the denominator, we are not going to have any horizontal asymptotes. So we'll say since the degree of the numerator is greater than the denominator, we can therefore conclude no horizontal asymptotes. In this case, for part B here, we can see that the bottom has a degree of, the numerator, the top has a degree of 2, and this has a degree of 3. So what we can conclude from this is we can conclude that since the degree of the numerator is less than the denominator, we will have a horizontal asymptote at y is equal to 0. And then for this guy here, so we look at this. Now we've got something kind of funny going on here. It's a +2. We're going to deal with that later, but first of all, I'm just going to ignore it. I'm going to look at this here because this is really the rational part, and then that's just an add-on constant. So what we have is we have the degree of the numerator is equal to 1, and we have the degree of the denominator equal 1. So because they're the same degree, since the degrees are the same, we can say y equals L is the horizontal asymptote. So what is L in this case? We have to look at the leading coefficient. So in that case, this guy right here is -3, and this guy here is 5. So the leading coefficient ratio will be -3/5. That will be my, that will be my horizontal asymptote. Okay, now we've got to actually deal with this. So we got to remember that all the things we talk about, they're all guidelines, but we still have to remember that adding 2 to a function is going to have a vertical shift up. So while you might be tempted to say that this would be our horizontal asymptote, we've got to shift up by 2 spaces. So we're actually going to go, the horizontal asymptote is located at y equals -3/5 plus 2. So that's adding 10/5, and then we have +7/5. So when we graph this bad boy, we should expect a horizontal asymptote at 7/5. Okay, I've totally cluttered this up, so let's actually just take a sec here and let's jump over to Desmos and make sure that this works. So 1 minus 3x. Okay, I'm going to just get rid of that. Okay, so 1 minus 3x divided by 5x plus 1, 5x plus 1, and then we're actually going to see, so right here, this is before I add the 2, y is equal to -3/5 will give me my horizontal asymptote, but if I add 2 to this function, the whole thing moves up by 2. So that means this is now going to go to 7/5, and that's where my horizontal asymptote is. So if we zoom way, way, way out, we can see that the graph levels off on both sides. There. One thing we can't determine is if it's slightly above or slightly below, and that's something we're going to look at a little bit later, but right now we can find that the horizontal asymptote is at 7/5. Okay, before we move on to the next example, I just want to take a second trying to actually explain what's going on here. So we said these lovely rules, but we didn't actually talk about either the rule. So the rule is this. When we're thinking about end behavior, remember end behavior always means as x goes to plus or minus infinity, what is y doing? So you can see that if the denominator is a larger degree than the numerator, that means as this guy goes to infinity, well, what's 1 divided by infinity? It's going to be 0. When you have a situation, even if it's more complex, if the degree on the bottom is bigger than the degree on the top, think about it. As this goes to infinity, this is going to infinity cubed. And as this is going to infinity, it's going to 4 times infinity. What's bigger, a really big number cubed or 4 times a big number? Turns out this one on the bottom grows faster. We're not saying it's actually infinity, because someone's going to say, oh, isn't infinity cubed just infinity? We're thinking, what if the numbers got really, really, really big? And big numbers cubed on the bottom are going to get bigger than big numbers on the top, just to the power of 1. So as long as the degree of the bottom here is larger than the top, it's going to grow faster. And when x gets really big, kind of big, over big cubed, that goes to 0. So as long as the denominator is a larger degree, it's always going to have a bigger number on the bottom for large values of x. In this situation, when the two are the same, I'm just going to erase that. When the two are the same, we're going to say 4x squared minus 2, 2x squared plus x. Think about when x gets really large. Does it really matter if we subtract 2? Not really. 4 times a million squared minus 2, who cares? This is negligible. This thing actually, I'm not going to use an equal sign, I'm going to write a squiggly. That's approximately equal to 4x squared if x is super large. Even the bottom, 2x squared plus x, yeah, x is worth something, but 2x squared is going to be way bigger. So I'm just going to ignore the 2 and the x. Any smaller degree terms basically don't matter. And at this point, we can say 4x squared over 2x squared. Well, it's kind of like we can cancel the x's. And this is 4 over 2. So if the degrees are the same, the numerator and denominator both grow at the same rate. All the smaller degree terms are negligible. We can just ignore them, and we can effectively cancel out the x's. That's why we can use the ratio of the leading coefficients. Same thing on the top here. In this case, if you have x cubed over x squared, well, the graph's actually going to end up looking like, basically, this is kind of like x cubed over x squared, which is kind of like x. I can actually guarantee you that the graph here would kind of go up on a slant. And in fact, it actually has a slant asymptote. We're not going to learn about slant asymptotes. It's just a little too much here. But it would have what's called a slant asymptote. Right now in this course, we're just going to stick with horizontal and vertical.